ML is a general-purpose functional programming language developed by Robin Milner and others in the early 1970s at the University of Edinburgh, whose syntax is inspired by ISWIM. Historically, ML stands for meta-language. It was conceived to develop proof tactics in the LCF theorem prover. It is known for its use of the Hindley-Milner type inference algorithm, which can automatically infer the types of most expressions without requiring explicit type annotations. Additionally, the use of this algorithm ensures type safety. There is a formal proof that a well-typed ML program does not cause runtime type errors. Overview. ML is often referred to as an impure functional language, because it allows side effects. Unlike purely functional programming languages such as Haskell, features of ML include a call-by-value evaluation strategy, first-class functions, automatic memory management through garbage collection, parametric polymorphism, static typing, type inference, algebraic data types, pattern matching, and exception handling. ML uses static scoping rules. Unlike Haskell, ML uses eager evaluation, which means that all sub-expressions are always evaluated. However, lazy evaluation can be achieved through the use of closures. Thus one can create and use infinite streams as in Haskell, but their expression is indirect. Today there are several languages in the ML family. The two major dialects are Standard ML and CAML, but others exist, including F#, a language that Microsoft supports for their .NET platform. Ideas from ML have influenced numerous other languages, like Haskell, Cyclone, Nemula, ATS, and Elm. ML's strengths are mostly applied in language design and manipulation, but it is a general-purpose language also used in bioinformatics, financial systems, and applications including a genealogical database, a peer-to-peer client, server program, etc. Examples. The following examples use the syntax of Standard ML. The other most widely used ML dialect, OCAML, differs in various insubstantial ways. Factorial. The factorial function expressed as pure ML. Fun FAC. Int equals 1, FAC. Int equals n asterisk FAC. This describes the factorial as a recursive function, with a single terminating base case. It is similar to the descriptions of factorials found in mathematics textbooks. Much of ML code is similar to mathematics in facility and syntax. Part of the definition shown is optional, and describes the types of this function. The notation T can be read as expression E has type T. For instance, the argument 10 is assigned type integer, and FAC, the result of applying FAC to the integer n, also has type integer. The function FAC as a whole then has type function from integer to integer. Thanks to type inference, the type annotations can be omitted and will be derived by the compiler. Rewritten without the type annotations, the example looks like fun FAC 0 equals 1, FAC n equals n asterisk FAC. The function also relies on pattern matching, an important part of ML programming. Note that parameters of a function are not necessarily in parentheses but separated by spaces. When the function's argument is 0, it will return the integer 1. For all other cases, the second line is tried. This is the recursion, and executes the function again until the base case is reached. This implementation of the factorial function is not guaranteed to terminate, since a negative argument causes an infinite descending chain of recursive calls. A more robust implementation would check for a non-negative argument before recursing, as follows. Fun fact n equals let fun FAC 0 equals 1, FAC n equals n asterisk FAC, and if then raise fail, negative argument, else FAC n. And the problematic case demonstrates a use of ML's exception system. The function can be improved further by writing its inner loop in a tail recursive style, such that the call stack need not grow in proportion to the number of function calls. This is achieved by adding an extra accumulator parameter to the inner function. At last, we arrive at fun factorial n equals let fun fac equals acc, fac equals fac, and if then raise fail, negative argument, else fac and list reverse the following. Function reverses the elements in a list. More precisely, it returns a new list whose elements are in reverse order compared to the given list. Fun reverse equals at x. This implementation of reverse, while correct and clear, is inefficient, requiring quadratic time for execution. The function can be rewritten to execute in linear time in the following more efficient, though less easy to read, style. Fun reverse xs equals let fun rev acc equals acc, rev acc equals rev tl in rev xs, and notably, this function is an example of parametric polymorphism. That is, it can consume lists whose elements have any type, and return lists of the same type. Books. The definition of standard ML, Robin Milner, Mads Tofte, Robert Harper, Vmit Press 1990, Vmit Press 1997, ISBN 0-262-63181-4. Commentary on Standard ML, Robin Milner, Mads Tofte, Vmit Press 1997, ISBN 0-262-63137-7. ML for the Working Programmer, Lawrence Paulson, Cambridge University Press 1991, 1996, ISBN 0-521-57050-6. Harper, Robert. Programming in Standard ML. Carnegie Mellon University. Elements of ML Programming. Jeffrey D. Ullman, Prentice Hall 1994-1998. ISBN 0-13-790387-1.